Okay, so welcome. Hello, hello. Hopefully we're live. Hello, 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 hello. Okay, so welcome. Hello, hello. Hopefully, nice. Okay, so I'll try to make this somewhat quick. I'm going to explain how to solve this problem. That's my best of ability. So as you can see on LeetCode, I was able to solve this, and I thought it was pretty difficult. So I'm going to talk about it. And so this problem is LeetCode hard, problem number 1000. And the description is, so it's minimum cost to merge stones. It's LeetCode hard. There are n piles of stones arranged in a row. The ith pile has stone of ith stones. A move consists of merging exactly k consecutive piles into one pile, and the cost of this move is equal to the total number of stones in these k piles. From the find the minimum cost to merge all piles of stones in one pile. If it is impossible, return -1. So this is kind of a difficult question. To give you some visual of what's going on here, and I'm going to save this guy. Let's give you an idea. Merge stones recap. 1. Give you an idea what's going on here. So one way of thinking about it is like, okay, let's say you have 1, 2, 3, 4, and 5, right? And let's say, so n is 5 and k is 3. I just have to be cognizant of my camera here. So if you suppose n is 5 and k is 3, what you can do is you could say, all right, let's merge these 3 into 6. All right, so I have 6, 4, and 5. And that cost us 6 to merge them. And let's merge these. And that gives us 15, costs 15. So 6 plus 15 is 21, right? And so our total cost to merge in this way is 21. But then we could say, okay, let's try merging a different way. Let's try merging here. So we have 12, 2 and 1, and that costs us 12. And we merge again, and we have 15. And that gives us 12 plus 15 equals 27. Now the thing to note is that 27 is larger than 21. So this is a better way to merge these values than this, right? And what they're asking for is what is, given a certain n number of numbers and an arbitrary k, what's the optimal way to merge these piles of things such that the sum at the end here is minimized? That's what they're asking, to make it kind of like really explicit and blunt. Try to explain it very quickly. The way they explain it though is it's like, well, you've got piles of stones, and so each pile has a certain number of stones in it, and you can represent that as a number, and then you're going to combine the piles of stones, and so when you can add them together, represent that as another number, and then each step is you're going to increment your total score by the size of that pile after you've added it together. And then at the end of it, you're supposed to put all the piles together, if it's possible, and try to find the way to do that that'll give you the smallest number, and then return that smallest number. So this problem is interesting, and I'll give you another example too. You can do like 1, 2, 3, 1, 2, 3, 1, 2, 3. It would be like n equals 9. And k equals 3, right? As an example. So you can go 6, 6, and 6 to give you 18, right? That's three different steps in one, and then 18 at the bottom to give you 36. And I believe that's optimal in this case. Now, the thing here to note is that this problem it's one of those problems that it's actually very easy once you realize how hard it is. It's one of those, and you can tell it's kind of difficult because it had, only 8,600 submissions in the first place. Only 8,600 people, shots were taken in the first place to even try it. And then of those very small number of submissions that were even tried, only a small fraction of them were even correct, this is like maybe less than a third, I'd say, of them were correct. Or no, excuse me, a little over less than a third, right? No. Times 3, this gives us 7.5. So it's less than a third. Yeah, less than a third of them were correct. Not very many people actually got this right. And the reason is it's actually one of those questions. It's a lot easier once you realize how hard it is. So if you decide to yourself, okay, there's not an easy way to do this, then you realize that the way to do it, there is a simple way to do it that is easy, but it's not efficient. And that's what they're looking for. They're not looking for an efficient answer. They're looking just for good enough in terms of efficiency. You see that the number of stones piles you have is only 30, and the size k is only 30 as well, and then the size of each pile is only 100. So the numbers you're dealing with are rather small, but they're too big to do exponential nor factorial time algorithms. So that's the key, is that this has got to be something that's between its polynomial time, ultimately, in the worst cases. But that gives you a lot of free reign. And the thing about LeetCode hard problems is a lot of them are thrown into that category because they're sort of these dynamic programming questions. And the thing about it is that they're not that difficult in a lot of ways. They're actually, in the sense that what you can do they become dynamic programming questions. So instead of solving it with an exponential time algorithm that sort of goes through all the different possibilities, there is some degree of overlap in terms of the function that you're calling, and you can do what's called memoizing. And that way, when you memoize your function, you'll end up not recomputing, what do they call that? Not recomputing redundant work. So there'll be redundant work that doesn't need to be recomputed again. That's all well and good. And that's pretty much the approach you take with this problem. I'm just going to get right into the solution. So that's the impetus. That's how you solve just about all of these LeetCode hard problems that are dynamic programming type problems. They're very difficult to do efficiently without dynamic programming. They're very difficult to do, period. But if you come up with an approach that can be memoized, that's essentially a recursive function, not a recursive function, just a solution that has sort of exponential branching type of thing, you'll find that a lot of the times those functions can be memoized, and they'll end up basically they'll be revisiting redundant work, and then the memoization will cause that redundant work not to be calculated more than once, and that'll give you a much better runtime than it would. Instead of exponential, it becomes some polynomial runtime. This problem, the other problem that I'm going to look at today, which is, I think, well, let's just say there's another problem we'll look at later, and I shouldn't say that. Let's just say this is a good example. This problem is a good example, one such thing, I would say. So we'll just get right to the solution to explain it. So, or actually, no, we'll explain how do we solve this. So, n equals 9, k equals 3 is a good example. So the first thing is we want to know whether or not it's possible to put these piles together. And what you'll notice is each time you put together a pile, you lose k piles, but you gain 1 pile. So you have a difference of 1 minus k. You see you have plus 1 minus k at each step. And you can write this in a way that if you take n and you do this q number of times, some number of times, you're going to end up with 1, right? So some positive integer q, some number of iterations later, you're going to end up with n plus this thing is equal to 1, right? You can rewrite this by saying n minus q of k minus 1 equals 1, and just say now q is a negative integer. And then that implies, or that's equivalent to, n is 1 modulo k minus 1, right? And that's kind of clear. So that's actually your condition for whether or not it's possible to put these piles together. Take n modulo k minus 1, is it 1? If it is, then it's possible. If it's not, then it's not possible. And a good example of this is, you can do like 6 and 4, right? So n is 6, k is 4, and you end up with 6 mod 3 is 0 mod 3. I'm going to write it this way, which is not 1. And you'll note, any way that you grab. Also, please note these are consecutive piles. I think it says that in the problem description. This is a very different problem. It's not consecutive. It's exactly k consecutive piles. It's like they bolded it. That's like a very important part of this. So you've got these piles. Okay, fine. There is a thing here, and that is, hold on. So you got these right. So that's a condition for what you can imagine, right? If you have 6 piles, anywhere you grab 4 and put them together, you'll have 3 piles left, right? You'll lose 4 and you'll have two piles, and then you'll add 1 more pile. So you have 3 piles left. You won't be able to put them together exactly 4 because you only have 3. So that's the basic idea, and it's pretty clear. It's pretty clear. Now let's consider, okay, so that gives you condition for whether or not it's possible. So here you go. Here's, and I think I also don't know, oh yeah. If you take modulo, if k is 1, actually if k is anything less than 2, then you should just not say, you should say it's not possible. That's sort of a sanity check. And then obviously if it's greater than 2, and this is the case, it's not, the modulo k minus 1 is not equal to 1. The number of stones you're working with, return -1. Okay, great. That's pretty straightforward. Now, this gets interesting though. This actually is it actually, what's the word? Is somewhat related to the part of the solution, the next piece that we're going to get into. So, what you can do is consider. First you got to suppose that this problem is too hard. First you say this problem is too hard. I don't know how to solve this problem. So let me concede that point and then try to solve it in like the easiest way possible, right? What would be the easiest way to solve this problem? Well, pretty much you're going to say, all right, it's too hard, so let me try to just do every possibility. Okay, what does that mean? Like, what do you mean? Like, let me try to do some kind of backtracking recursion shenanigans. Like, let me try that. So what that comes down to is that you say, okay, let me try to break this into 3 piles, right? And then for every possible way I can break this up into 3 piles, like k piles specifically, for every possible way I could break it up into those piles, I'm going to recurse on every one of those possibilities, and the result of all those possibilities, so you recurse on each of these, and you get some number, and you add that number together, and so each of those numbers is going to give you what it costs you to combine each of those. So like basically you call the function itself on each of those, and then if you add all that together, that's the cost for each of these to be combined, and then after you've got that, you've got to add the sum over that entire interval to that, if that makes sense. So there's sort of like f of 1 2 3 1 2 3, f of 3, oops, 3, and then finally f of 1 2 3 3, right? And you add all that together. So you get each of these things. You add all those together, right? You add all those together, and then you also add the sum of the whole interval. 1 2 3 1 2 3 1 2 3. Right. Okay. Now, why do you do that? The reason you do this is what you're going to do is you're going to recurse on each of these cases, and that's going to tell you, right, the cost to combine just that piece, each of those pieces, right? So each of those pieces, you combine them, and then you have to actually, so you get each individual piece, then you got to put all that big pile together. That's this piece, and add that to the sum you got. So there's a sum for each of those individual pieces. You add those all together, and then you get this sum over the whole interval, and you add that on top. And actually, this gives you pretty straightforward recursion. The only problem is that at each step, you need to get every possible. So what you've got to do, though, is you've got to get, for every possible sequence, you've got to perform this recursion, right? And then get the smallest number at the end of it, right? And actually, every possible thing that you get, it's the same sum, so you only have to do that at the end. You don't need to do that at each step. In other words, for each possible sequence of splitting up the piles into k subdivisions, you don't need to continuously add the sum over the whole interval on every possible calculation for the subsequences of the subdivisions, if that makes sense. And actually, what that is borne out to in the code is, instead of putting this sum here, so you could put it right at the bottom of the return, or you could put it right here when you're, or rather here at the total. You could add it to the total at the bottom here. You could do either here or here. It's not going to change which sum over the subsequences is the smallest sum. So, okay, great. So now the problem is, okay, you may notice something here, and you may say, okay, well, that's all well and good, but how do we actually get all these different subsequences? So that's ultimately what the solution is. It's just what I just described, and then memoized. And we also run another routine, right? Another routine to generate that list of subsequences. So to generate the list of subsequences, you may have noticed, and again, so this is where I was saying this piece informs that. If we go 1, 2, 3, 1, 2, 3, 1, 2, 3, right? You could say, okay, you have a pile of 3, then you've got a pile of 5, then you get a pile of 7, then you get a pile of 9. And what that comes from is all of the solutions that are possible, right? You add k minus 1 to each piece. So you have 3 works, you get add k minus 1, which is 2. 5 works, add another k minus 1. 7 works, etc. So you simply add k plus 1 each time to create the next, sort of size for the pile. Now things get kind of interesting here, because let me see something here. Let's do a new one, and let's put it all the way here, and let's save this. Merge stones recap 2. Now things get kind of interesting here, because what we want to do is say, okay, we're looking at 3, 5, 7, 9. The problem, though, is that this function needs to return all of the subsequences. So this function is actually more interesting than the other one, because it's a little more involved. It's actually a backtracking algorithm, and it's going to hit every possibility. How many of those possibilities are there? I don't actually know. See, I'm not sure how much this algorithm explodes in terms of time complexity, because I just don't know. Like, it's actually it's just unknown to me. The numbers that we're working with apparently are small enough where, like, when I entered the solution, it was correct. But it's literally just a backtracking question, where you say, okay, you've got a certain number of piles, right? And so we're going to say, okay, pick 3 as one of the piles. And then we're going to recurse here to determine, we're just going to try to get 2 piles now with these elements, and k is 3, right? And then you can say, okay, we'll put 1 pile here, and then that leaves the other pile there on the backtracking. And then you can say a pile here, and that leaves the other pile there. And you can say piles here, and then piles there. And continuing with that idea, you can go 5 and say, okay, pile here, pile there, or pile here, pile there. And what I ended up choosing was, right, just simple backtracking, which basically means you make a choice and recurse on you explore with that choice being chosen, then unchoose that thing and continue. And actually, that's it. Believe it or not, you make a choice, then you recurse on what's left, and then you're actually done. I mean, you still have to choose all the other choices as well, but you sort of unchoose the choice you had. And the way I ended up doing it, I think I used a stack. So I used an array, and I would push this element onto the stack. It wasn't really the element that I'd push a position. So I push this position onto the stack and recurse. And then after I recurse and get all those possibilities, I would then pop that from the stack and then push this onto the stack, this position, and then continue in that way. I think each recursion you would have. I think I would push a start position and an ending position, so I'd sort of have like a start position and end position that I recurse on, and the things I'd push onto the stack were actually tuples, I think. Let me see. I think there were tuples that I pushed. Yes, yeah, to keep things kind of straightforward. The thing, though, is that I had a kind of an interesting base case to remove the cases that that couldn't possibly work. So obviously, if you have more piles, but you're recursing on something that's empty, that's not going to give you any solution. So you just return there. Sometimes you would actually sometimes you would actually recurse in such a way where you would have all your piles are finished, but you wouldn't get all the way to the end. Obviously, that's not a solution either. So those cases get thrown out. So this is a case. So here we actually check that we make it all the way to the end, and if we do, then we append. Here we also check. We prune the branches that are and obviously we prune the branch too. Once we've, well, it's actually the leaf already. We prune branches that we that fail this check, and also prune branches that go over, right? So that's kind of an interesting base case because it's some pruning going on there. But yeah, it's simple backtracking. Just select. You loop over for the position, the start position, and the target. So there's a certain start position, and then there's a target position, and then you just loop adding k minus 1, and recursing, append that to the stack, recurse, and then pop from the stack. And obviously you would select x plus 1, so you would. I think I may have programmed it in kind of a weird way. I think I started with, I would actually add 1 to x. So x would start at the start position. It really should be, oh, I see. Oh, that's probably why. Okay, it really should have been, x should have been in start position plus 1 to, well, no, see, that's the thing, right? Because you could recurse with just the start position equal to x. So this was actually fine. It's just when you recurse, recurse x plus 1, meaning you would recurse on the thing after. No, that was correct. Yeah, that's correct. You would recurse on what's left after afterwards. Yeah, interesting. Yeah, pretty neat. Pretty neat. So that's it. That's what we would do, and then obviously we use some non-locals for this recursion. Kind of a funky thing you can, not a funky thing, but an interesting thing you can do with Python when you're dealing with what they call, oh, this is actually very interesting what I did here. These both should have been cached. Wait a minute, I wonder what happens if I do this. Hold on. Is this any faster? that's wrong now. Oops. Oh, I take it back. Whoops. Whoops. Oh boy. Wait a minute. Interesting. What? What do we do? Oh. That's very funny. Huh. So something kind of strange happened there. This doesn't return anything, this function. Oh, that's very interesting. All right. Well, huh. Uh-huh. Wow. I don't know. I'm not entirely sure what to think about this now in terms of the time complexity. Because this part's not memoized. This is. But that doesn't actually matter that much. Well, it kind of matters. Oh, no, it does matter. It matters a lot. Yeah, this actually matters a lot. Because this gets called a bunch of times. I'm actually not entirely certain how much time... I don't know what the time complexity of this is. I don't know. I do not know. I want to say it's something like k times p times like... No, it's something... I want to say some polynomial time. I don't know. I don't know what it is. I think it's polynomial. But anyway, yeah, I'm not entirely sure what the time complexity is, but it's kind of a neat thing you can do. You can have sort of a non-local variable that is effectively a static variable that's sort of just outside the function, and then you can modify that static variable so you can just keep pushing stuff onto the... You can have this stack that just is constantly being used, and then you can push all the results onto this return. And then you can even call your auxiliary recursion function and then return what's returned afterwards in another auxiliary function, which is also a local function, which you can use an LRU cache to memoize it in a very clean way, which is just func_tools LRU cache. And then you can, now the actual algorithm, so that part just gives us all of the splits. So that'll give us a bunch of tuples for like where this is split. So like, you know, this might be a tuple, like 1, 3. And then this might be a tuple 1, 3. Or sorry, 4, 0, 1, 2, 3 should be 0, 2, I think. And this might be a tuple 3, 4, 5, 3, 5. And then this might be tuple 6, 7, 8. Right? Yeah, 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So those things, right? So that could be a tuple, and what'll happen is this is going to give you all the possible tuples that we're interested in, all the different ways you could split into k piles. And then, so what you can do is you do exactly as I described, is that, you know, just make sure you're not over, you know, the sort of more of a sanity check. But it also checks if the position, if it's a pile, it's a single element. What it's going to do is it's going to call that other previous function to give that list of different sequences, different piles. We have our initial return what we're going to return is just initially negative infinity. And we say, okay, for each sequence in that list of sequences, set the total to 0, get that for that A, B pile, that tuple, in that pile in that sequence. You're going to call our initial function recursively. So we're going to find the solution to that, add it to the total, increment the total, and then we're going to say, we're going to do that for every pile, right? So as described, so you recurse on every pile, add it to the total. And then you're going to change return to the minimum of return and the, oh, it's not negative infinity, it's positive infinity, and the total. So the first thing you see is going to replace the positive infinity. That's why we set it to positive infinity initially. And so you do that over and over for all the possible sequences. So you recurse on all the subsequences and get the whole sum, right? And you get the smallest possible sum over all those possibilities. And then at the end of that, we have this little piece down here, which adds up everything in over the interval that you're looking at. And there's a little bit of code here to kind of optimize this a bit. It's not particularly important that this is optimized because this can actually be done. This can actually be done like in tandem with the rest of the algorithm. But I thought it'd be just simpler to do it this way. And the way you do this is you use what's called prefix sums. So the way prefix sums work is you just make a sum that looks like this. Like so for this case, you'd have like 1, 3, 6, 7, 9, 12, 13, 15, 18, right? That would be your prefix sums. Let's try again. All right, so yeah, so you've got these prefix sums, right? What you do to determine what's the sum over a certain interval in constant time once you've done this pre-processing step is you just take the difference between, you take this sum minus this sum and add back the element there, right? So what'll happen is you'll end up with these numbers added together, subtract what's here, you end up with what's left over is this sum over this interval, which is like, I guess 1, 2, 3, 4 is like this guy, right? So 7 minus 3 gives you 4, and then you add back the 2 to give you inclusive. So here, from this position to this position, which is from 1 to 3, the sum is 6, right? So you do 7 minus 3 is 4, and then add the 2 back to get 6. It's kind of takes a little bit. Kind of got to like wrap your brain around that a little bit initially, but if you think about it enough, it'll still start to make sense. Basically, it's a whole bunch of numbers are added together at this position, and then you remove a whole chunk of those numbers from this position, but you also end up removing the element at that position. So you got to add it back. That's it in English. And so that's exactly what we do here. We take, you could inline this to get the sum over the interval, but yeah, it's the prefix sum of the furthest position minus the position closest to the left, furthest to the right position closest to the left, and then add back that position closest to the left to get the total sum over the interval, and then just add that to your return value and return it, and you're done. And obviously it gets a little confusing because all this is recursive, so you have to factor in like, oh, this is being done at every step, so like what does that mean? That's also why we have 0 here. So at the base case, we only consider single piles. Basically, it doesn't cost anything to put them together. That's our reasoning. So single piles give you 0, and then when you combine that over an interval, so if you were to call this over an interval, it would recurse. It would actually just give you 0. Actually, the solution would just flat out give you 0 if n was 1, which I think is correct actually, because you don't have to combine anything. So you're just done immediately. So yeah, that's it. That's the whole solution in one simple explanation. Not the fastest one, but sufficient. So yeah, you can go over the solutions when you're done. But that's my solution, and I wanted to go over that, officially, publicly, whatever. So hopefully other people can understand what's going on there. But the basic idea is you've got one recursive function that'll break this up into the different sequences that you can have, different piles, and then a second recursive function will actually loop through that sequence of piles once you've got it, and produce a result, a solution, based off of the sequences of piles recursively. And it will also, yeah, it's kind of cool in the sense though it's like it's a recursive function that calls another recursive function. But it's not that interesting because this could just be another function that returns the sequences. Like it doesn't have to be a recursive function. But yeah, so yeah, this is sort of simple memoized recursion, whereas this is some backtracking that's also memoized. Now the thing is, you might think this doesn't do much, but this actually matters a lot because this gets called as part of the recursion. So the memoization is kind of complicated. That's also why I was saying, like, I'm not actually sure how this factors into like how expensive the algorithm is. I know it's polynomial time. Obviously, it's fast enough, but it's like I don't actually know what the total runtime is. The worst case runtime. I don't know. I think it's polynomial. I want to say it's polynomial. It could not be also because of this. Obviously, when I tried to memoize this thing, well, this doesn't have a return value, so it shouldn't have mattered. Well, it did matter because it'll actually truncate the recursion and cause problems like backtracking. All right, so let's move on to the next one. So that should be like relatively quick explanation. Hopefully, quick enough. Okay, thanks for watching, and we'll go to the next one.